Finally, the moment we've all been waiting for. We're going to get our hands dirty here doing some real quantum computing, or at least some simulated quantum computing, as close to real as we're going to get here. All the notebooks and examples we're going to work through will be made available to all y'all. We'll send out the slides afterwards, and there's URLs on there. So if you don't want to follow along at home or right now, you can take these home and do more quantum programming there. So by way of quick introduction, I'm an assistant professor in computer science in Vanderbilt University down in Nashville. And Yushin, who is floating around the room here helping out, was previously my intern there, and she's now a grad student at USC. So if you have any questions, raise your hand, shout at us, throw things at us, whatever you feel is appropriate, and I will try to help out, or Yushin will be floating around to help make sure everybody's able to run stuff. Again, if you have a laptop, something that's capable of opening a web browser, you should be able to follow along here with us as we journey through the quantum realm. But if not, you'll have all the URLs and stuff available for later. All right, so we've heard about Qiskit a lot so far, referenced in various talks throughout the past couple days here. But just to refresh or dive in, what is it? So it's an open source quantum computing framework, which is nice. You can see how all the sausage is made, developed by IBM. And everything that you can do with Qiskit is based in Python. So as I mentioned during my little teaser this morning, so the language of quantum computing is linear algebra largely, but also largely Python. Kate, during her talk, mentioned there's some other libraries come out in different languages, but Python is really one of the big ones. One of the nice things about Qiskit is that it provides access to both real quantum hardware as well as simulators. So we'll use some simulators in this example, but if you want, it's a pretty simple extra step, if you want to do this after the fact, to actually run on some real IBM hardware. And IBM gives you, 10 minutes of free quantum credits, which is a lot for a quantum computer. So, all right, but enough lecturing. Let's actually try to dive in here. So, a quick preview of sort of what the life cycle looks like to work with Qiskit, okay? So the first step is going to be common to whatever library you're using. This is not Qiskit specific. You have to tell us what is the problem you're trying to solve. So you have to actually specify in code what is the quantum circuit that you want to run, right? That's pretty uncontroversial. The next step, which we aren't going to dwell on too much, we'll see it a little bit in the notebooks, but we're not really going to dwell on it, is to optimize this circuit. So this is mentioned a little bit like during Kate's talk this morning, but depending on the particular hardware or simulator you're running on, there might be different basis gates available or different types of things you want to do to optimize your circuit. For example, if you have a circuit that has two X gates sequentially. I mentioned X gates during my little teaser. An X gate is sort of like a quantum analog of a NOT gate. It'll flip your two probability amplitudes on a single qubit in the computational basis. So if you have two X gates in a row, it's idempotent. I can use math words here, right? So those two things should cancel out, and we can optimize those away. So there's some optimization passes involved with more realistic circuits. We won't dwell on it too much. But the most exciting part is actually executing the circuit. You've defined it, okay, it's all set to go on your particular architecture. You want to run the circuit, right? And so there's a few different classes within Qiskit to actually run this, the circuit on some hardware or simulators. And then lastly, back in Python land, we'll just do some post-processing to visualize or output or analyze the results. So one thing to note is that really only step 3 is really the only place where the quantum stuff is happening. You have to know what is going on. You have to understand the quantum things to do all the other steps. But really step 3 is where the actual execution of quantum computing is happening. All right, so with that, let's go ahead and jump into our first little tutorial notebook here. I've got the URL up on the slides here. This is hopefully big enough for everybody to see, but this is tinyurl.com/YETRTB48. This is going to be a read-only notebook, so feel free to mess around, make changes, obliterate this thing. You will not break it for other people. So, right, so if you, I'll switch over here. Let's see, does anybody need the URL still, or we got it? See some heads nodding. All right, and Yushin is floating around in case you didn't catch the URL. So let me click over to here. All right, so yeah, so this is a read-only notebook. If you'd like to save your own copy, save some changes, or play around with this later, just click on File, the File menu at the top. You can save a copy in your own Google Drive or to GitHub or whatever you please. but feel free, this is safe. There's a lot of text in these notebooks that we've put as like a reference. I'm just going to narrate, so I'm not going to read this. I don't expect you to read all the text either, but if you're a visual learner or if you want to look at this later at home, there is plenty of text in there as well. So the first step that we're going to run, by the way, I should poll the audience here. Has anybody used Google Colab before? Do we have any Colab users? Okay, good number of you, right? So Colab is a hosted version of like Jupyter notebooks, which are really popular in Python. And if anybody's used, Mathematica, we have a lot of mathematicians on the audience, right? They have these sort of like Wolfram notebooks, same idea, same kind of format. You can ignore any security warnings and just trust me, right? I promise, it's fine. But each of these computational cells, you can run them. There's a little play button next to the cell, so you can just click that and it'll run whatever code is in here. So the first step we need to do is just install all the packages we need, and this is the slowest step. This will take a second, but we'll let it do its thing and run. There's a whole bunch of output there. In this case, I just ran this notebook in the other room, so we're all set to go. So now I can go ahead and look at the next cell where we're going to go ahead and write some actual code that's not just installing packages. So what I've done here is, first of all, imported a class called quantum circuit from Qiskit. One of the nice things about Qiskit is that things are generally as labeled on the box. So the quantum circuit class represents a quantum circuit. Not a huge surprise. Here we go. So we're going to create a quantum circuit by calling the constructor of that class. And the simplest constructor for the quantum circuit class just takes one argument. It takes how many qubits are in your circuit. So for this just simple demo, we're just going to have 1 qubit. So pass in a 1 there, and there we go. We'll also apply 1 gate. So one thing that's sort of nice about the notation here with Qiskit is the way you add a gate to your circuit is to call a particular gate function on your circuit object. So you read this in English as saying, on my quantum circuit, QC, apply an X gate to the 0th qubit. This is all Python, so things are 0 indexed, right? So I might say first qubit accidentally, but the 0th qubit is the first one there. Right, so this will apply an X gate to the 0th qubit, which is sort of that quantum analog of a NOT gate. And then one of the really nice things about Qiskit is its visualization capabilities. So we can draw these circuits in a really nice way. So we'll go ahead and draw them using the matplotlib backend. And let's just run this thing and see what happens. All right. Here's the world's smallest, saddest quantum circuit. Here it is. We don't even have a measurement operator yet. We'll get there. But we've got a little qubit, just Q here. There's only one of them, so Qiskit isn't even indexing this. It's just calling it Q. And you can see we've got this little line where we apply an X gate to the qubit. All right, any questions so far? Again, I'm going to talk quickly, but raise hands, shout, throw things. It's all fair game. Yes, question? You have to use X when you're doing it. Yeah, so X is the X gate. So it's the specific name of a gate, and Qiskit has a bunch of these built in. So like Z is built in, H is built in as like the Hadamard gate. There's a bunch of these that are built in. And if you want a custom one, you can do that as well. But Qiskit has a bunch of these primitive gates built in. Good question. Awesome. All right, we'll keep cruising then. There's some troubleshooting steps if you want to run this at home. We'll go ahead and build a slightly more exciting circuit here for our basic demo. Whoops. We'll make the a 2-qubit Bell state. So 2-qubit Bell state, first of all, is going to involve 2, not 1 qubit. And when we measure this state, there are going to be 2 of the 4 possible 2-qubit states that we observe with equal probability. So in and of itself, this is not super useful, but Bell states are used as sort of foundations or kernels in a lot of quantum algorithms. So we'll just look at how to prepare this state, and that's a simple little circuit. So we'll go ahead and make some imports that we need. That's that cell. And now we need to actually build this more complicated circuit. So there's a little bit of math, which we've had 3 days of mathematical things. I'll just sort of skim over. But the way that you do this, you can check. It's 4x4 matrices, so you can check this on paper if you want. But the way you generate this state is applying a Hadamard gate, to the 0th qubit, and then apply a control NOT gate between qubits 0 and 1. So this will get you the state you want. I'll wave my hands and say, take my word for it. But I will pay more attention to the code here. So I want to create a new circuit this time. And so I call my quantum circuit constructor. I'm going to initialize it with 2 qubits. Now this time I'm going to try to measure some results. And when I measure things, Qiskit requires that you explicitly specify how many classical bits of information do you want to measure, or how many qubits do you want to measure. So there's a second parameter here, which is also 2, because, unsurprisingly for me, I want to measure both qubits and see what's up. There are legitimate algorithms where you don't need to measure all the qubits or things like that. But in this case, we will measure all of them. So that's that second parameter there. So then, to the earlier question, here's an example of building a circuit where we're using another gate type. Qiskit calls the C0 gate the CX. This is sort of their notation for it. And you say the control qubit is 1, the control qubit is 0, the target qubit is 1. And the order in which you write this code matters, right? So your Hadamard gate gets applied to the circuit first, then there's the C0 gate that gets applied to the circuit. So no surprises, code runs in linear order. The other thing we're going to add to the end of the circuit here is a measurement operator. So that's done by this measure function in Qiskit. The parameters here specify first the qubits that we're going to measure, and the second argument here are the classical registers, the classical bits that are going to store the results of those measurements. So this says measure qubit 0 and put the result into classical register 0, and then measure qubit number 1 and put that result into classical bit or classical variable number 1. Again, not really surprising too much for a simple little circuit, but that's the deal there. And of course, we can go ahead and draw the circuit and see what it looks like. Pictures help. So we've got a Hadamard, a C0, and then our 2 measurements. You can see how Qiskit draws the measurement operators. We have our little measury things, and you can see it creates this imaginary thing that's our classical register of size 2. We have 2 numbers that we're going to store at the end, and qubit 0 gets put into classical bit 0, and qubit 1's value gets put into classical register number 1. All right. And just mathematically, here's the state that we're going to prepare. So even superposition of 0, 0 and 1, 1, the 2 pure states there. All right. So that's defined our circuit. Again, I'm going to breeze right by optimizing the circuit because there's nothing really to optimize here. We only have 2 gates. This is as good as it gets. We'll just keep cruising ahead to the fun part where we actually run the circuit. Let's do some quantum computing. So we're going to use a simulator. As mentioned, if you want to run on real hardware, we can help you out after the tutorial or email us as a follow-up. Pretty simple. But we'll create this error simulator object. Qiskit has a few different simulators built in. The error simulator is sort of the default recommended simulator object. So we'll go ahead and create that as our what we'll call backend. Now we run this transpile function. This is what optimizes your circuit. As I said, this is really not going to do anything for this circuit, so we won't talk about it. But as good practice, I'll leave it in there. You transpile or compile your particular circuit to run on that particular backend that you've initialized. So now we have our compiled circuit ready to run. And what will we do? We'll use our backend to run the circuit. That's sort of like the mental model here. So this run function, how we actually execute our job, is a function on our backend. So we use our backend to run our circuit is the first parameter. One extra interesting parameter here is shots. This is the number of times we're going to run our circuit overall. So as with any quantum algorithm, there's some probabilistic kind of weirdness, right? You might not get the right answer every time, and you want to run a bunch of times and then take the most popular result or something like that. So we'll run this whole algorithm 1,000 times to see what happens. And then Qiskit has a few different functions built in to get a dictionary and a histogram of the results. So that's what this counts object will be. We'll go ahead and run this and take a look. So there we go. When we run our simple circuit, we get a dictionary of our results. And we see that out of our 1,000 trials, 493 times we measured the 1, 1 state, and 507 times we measured the 0, 0 state. So that's good. That means our circuit worked. We saw only the states that we wanted, 0, 0 and 1, 1, approximately half of the time. Note it's not exactly, but approximately half of the time. And we saw the states we didn't want exactly 0% of the time. And one last thing here, Qiskit has a nice function built in called plot histogram, where you pass in a dictionary of your results. And it does what it says on the box, plots a little histogram here of the counts versus the individual quantum states. Okay, any questions on that piece so far? Yeah. Oh, you get an error. All right. Yushin will run over to help while we're talking. Excellent. Other questions? Yes, sir. Yeah, great questions. Circuit optimization is a whole area of research, applied math research, sort of the stuff I was hinting at this morning, so it's a thing. But generally, the metrics that people look at are the total number of gates in your circuit, so can you reduce the number of gates? And then another metric is the total number of C0 gates, so like which are like multi-qubit gates. So some people care more about, like, I don't care if you have a lot of single qubit gates, I just don't want multi-qubit gates or things like that. But those are really the two metrics, like gate count and C0 gate count.
Yeah, so I might even think that depth would be another one of interest, but...
Yeah, depth, number of gates is sort of a proxy for depth as well. But when you get into these big circuits, it's a close enough proxy where you can just look at the number of gates and realize, okay, I've got a shorter depth. But yeah, open area of research. Excellent. All right, well, great questions. Thanks for staying awake with me here. This is our basic demo. We've done some quantum computing, and now we're going to jump ahead. So we will actually do a real-life, honest-to-goodness textbook quantum algorithm here, and we'll see, we'll put this to the test. Is everything we've learned the past 3 days a total lie, or is quantum computing actually real? Can we actually do it? So we'll test out Grover's algorithm. Grover's algorithm we've heard a few times, but just to state it formally, put it on the slide in case anybody is more on the quantum curious end of the spectrum here. We'll have a query function f, and this query function f is going to be equal to 1 for our special value that we're trying to find, and it's going to be equal to 0 otherwise. So for example, maybe we're trying to find a particular entry omega in some unsorted database. And the cool punchline, which you've heard with Grover's algorithm, is, rather than having to look at, on average, n over 2 things to find your specific entry, Grover's can run with order of square root of n number of steps. So you get a quadratic speedup over classical algorithms. We won't dwell on the math, but we'll just appreciate good old Grover's algorithm. I'll give you a quick, very, very hand-wavy, non-mathematical overview of Grover's algorithm. There are probably half the people in this room can explain Grover's better than I, if we want to dwell into it, dive into the math. But I'll just quickly give you a flavor of it so that when we switch to the code, we're not totally disoriented. So the idea of Grover's algorithm, the key thing is that we have this magical quantum oracle, which is an interesting assumption that is something worth thinking about when we look at the algorithm. But we have an oracle that will mark our target states. So if there's a particular state x, that's the thing that I'm trying to find, this magical oracle operator, which is a unitary operator u, will flip the phase of my target state of the thing that I'm looking for, and it'll leave everything else alone. Okay, so take that as an assumption that we'll have this magical operator. We'll show an example of how we actually define it in code. We'll have an operator that does this. And there are actual ways to implement this, otherwise the code would not work. So we'll see that in a second. So in addition to that, assuming we have that oracle, the way that Grover's algorithm basically works is this amplitude amplification trick. And again, I'm not going to tell you the math, but there are slides, there are books, there are experts here, right? But pictorially, on every iteration of Grover's algorithm, you flip the phase. You do this phase flip of the states that you care about. And then you do some tricky averaging and inversions about the average using reflection operations and reflection math in such a way that after one pass, the amplitude of your target state will actually end up higher than the amplitudes of any of your other states. So all else being equal in the beginning, at the end of one of these Grover iterations, your marked states actually get a slightly higher probability amplitude. Again, I'm skipping the math and the why a little bit, but that's fine. The key is, if you repeat this trick, this amplitude amplification trick, where you mark the flip states and do this trick about square root of n times, the probability of getting the right answer, seeing the marked states that you want, goes to 1, or gets pretty close to 1. So this is sort of the idea. So Grover's algorithm, high-level overview here, initialize all of your state as just zeros everywhere, and then Hadamard all those things together. Doing that gets you an even superposition of all of the possible bit strings of length n. So we'll show a 3-qubit example of Grover's here, so you'll have an even possible blend of observing all 8 2 to the 3 possible different states. Then the magic number t times, which is something like pi over 4 square root of n, t times, you apply this Grover's operator, which is a phase flip and an amplitude amplification, and it has some proper mathematical form. You can implement it if you want. You do that the right number of times, and then you just measure at the end. And odds are you'll get the marked states that you want to see. When I say repeat this operation, the Grover's iterate t times, it literally looks like you take this thing in curly brackets here, this chunk of the quantum circuit, and just repeat it from your left to right over and over in the circuit t times. So we'll see how that looks in the code as well, but it's literally just copy paste this magic chunk of quantum gates t times, and then measure everything at the end, and that's Grover's algorithm. So again, very hand wavy, but just to give you a flavor of what the code is going to look like. All right, so as mentioned, I'm going to show now an example of running Grover's algorithm on a 3-qubit system. So we have 8 possible states, and we'll run this where we have 2 marked states, 0, 1, 1, and 1, 0, 0. I just picked 2 arbitrary ones out of our 8 possible states, and these will be the things that we're looking for, and we'll see if with Grover's algorithm we can find them. So again, we've got a tiny URL here for the Google Colab notebook. This is tinyurl.com/b37ez2xm, b37ez2xm. And we'll give everybody a second to pull that up, and Yushin can help you grab the URL if you need it. All right, so as before, the first cell in this notebook is just going to be installing the dependencies that we need. Hopefully these will all be cached for me, and we'll go quickly here. All right, perfect. So I've got all those. We can jump right in and get into doing our Python imports. There's not a lot going on here in this box, but one interesting thing to note, which we'll use, is we're importing something called Grover operator, a class from the Qiskit circuit library submodule or subpackage. So Qiskit, in all of its infinite wisdom, realized like, hey, there's probably a lot of people that are going to be giving tutorials or using Grover's operator, right? But Grover's operator is also, it comes up in other algorithms too. So within this library of pre-made operators, Qiskit's given us this Grover operator, which is another reason I skimmed over some of the math. Like, it's already largely given to us here by Qiskit, which is real nice. Most of the other imports here we've seen before. So okay, so now we need to go ahead and set up our problem. So that in this next box, we're defining a function called Grover oracle. And this function takes in a parameter that's a list of the states that we want to mark. So I think what did I say, 0, 1, 1, and 1, 0, 0. We'll take in that list of marked states, and then we're going to build an operator, our UF, so a little chunk of our quantum circuit, that's going to flip the phase of our marked states and leave the other ones alone. So again, we won't go into a ton of the math here, but I'll at least show you what that code looks like, and then how we take this chunk of a circuit and compose it into our overall circuit for Grover's algorithm. So we figure out how many qubits we have. We can initialize our little chunk of a circuit here, which is going to act on 3 qubits in this case. That's how many we have in our example. And then for each of our marked states, we need to do a little bit of quantum stuff to flip their phases. That's the idea. There's one gotcha with Qiskit that I want to call out, which is that when I tell you a bit string like 100 or 011, something like that, the order in which I'd say that or write that on the whiteboard or that you'd write on the whiteboard is the opposite order that Qiskit is actually storing the qubits in. So if you want to reference the state 100, Qiskit needs you to actually reverse that. So there's a little bit of Python niceness here, Python syntax to reverse our bit string. This little syntax gets you the string in the reverse order. But this is just a heads up. If you're ever using Qiskit in your life and you're working with a bit string like a 100 or something, and you want to refer to the correct qubits, there is this little gotcha about making sure you have the bit ordering correct. So with that disclaimer in mind, The rest of this I can largely gloss over. So this math here, there's some X gates, some Z gates, some things like this. This is the one implementation of the actual gates that will flip the phase of anything in our target state. Again, I'll sort of skip over the math and ask you to trust me on that. But I'll just tell you that we're building up this little chunk of a quantum circuit that will flip the phase of each of our target states. So if you believe me on that, we can go ahead and look a little more closely at the remainder of our circuit here. First, I'll show an example of we define our marked states. So here we are, 0, 1, 1, 1, 0, 0. And then we'll create this little Grover oracle, the UF, and draw it and see sort of how it looks. One thing to note is that the oracle that we create depends on the marked states. That was one of the inputs to that function. So if we were searching for other stuff in our list or in our database, our oracle would look similar structure, but slightly different. It'd be operating on slightly different qubits and things like that. So that's our oracle UF that does the phase flipping. But we need some more stuff. In addition to the phase flipping, we need to do the amplitude amplification step. And for that, we'll use our Grover operator class that's been provided to us from Qiskit. The Grover operator class takes in an oracle as input to its constructor. So we'll pass that in, and now we'll show what that looks like. So now things start to get complicated, right? Now we have a lot of gates and stuff in our circuit. You can get a sense of, okay, maybe some optimization and stuff starts to be sort of useful here. Right, so now this is a chunk of a circuit that's doing both phase flipping and amplitude amplification. But if you recall from a couple minutes ago, this is not quite enough to do Grover's algorithm. This is one iteration of Grover's algorithm. This is Grover's iterate. But we need to take some number of copies of this and assemble this into a circuit and also prepare our state and also measure our output at the end. Okay, so we do a little math to compute the optimal number of iterations. You can prove this at home. It takes about 2 or 3 whiteboards of math. I had to do this when I taught QC last spring. You can do it. It takes some time, but there's signs and rotations. It's a cute little proof. Okay, but what I will pay attention to now here is assembling our final ultimate form, the entire Grover's algorithm circuit. Here we go. So as before, our overall circuit here is going to have operating on 3 qubits. The first thing we do is Hadamard all of our qubits so that they're all in an even superposition of all possible 8 basis states. And there's some little nice Python syntax in here where you can just say do an H on all of my qubits. You could also say qc.h0 and then qc.h1 and then qc.h2. But Qiskit has some support for some nicer Python syntax if you want to do operations on multiple qubits at once. Then we're going to assemble our circuit, so, the rest of our circuit. So after we've Hadamarded everything, we're going to use this compose function from Qiskit. Compose is like a stitching operator. So you have your circuit and you just stitch on some other stuff, stitch on another piece of a circuit. So we'll compose with our existing circuit a power of our Grover operator circuit. Power is sort of like exponentiation. You do a particular circuit, k times or whatever, sort of abusing the exponent power notation a little bit, like Grover op to the n or whatever. So we'll repeat this circuit the optimal number of times, this part of the circuit, the optimal number of times, and then we'll stitch all that together. So we'll show what this final circuit looks like in a second, but the last thing is we'll measure all of our qubits. In our basic example, I showed just measuring 1 or 2 qubits individually, but here we can use this nice helper function in Qiskit to measure all of them. If I go ahead and draw the circuit, Qiskit gets a little mad and just says, there's stuff in here. This is where you're doing the Grover's operator the appropriate number of times. So it abbreviates that for us so that this can fit on the screen. But you can see we've got all our Hadamards. Then we do the Grover's iterate stuff, t times, the optimal number of times. Then there's this little logical divider for just visual purposes. And then we measure everything. Each qubit goes into the corresponding classical bit in our classical register of results. All right. So that's building the circuit. Any questions there? There's obviously a lot of hand waving in the math, but any questions on, or anybody stuck on sort of the Qiskit side? Yes, sir. Yeah. Yeah, it's related to like the. Yeah. The question is, why is it called the Grover diffusion operator? And I believe the intuition there is you're sort of diffusing all of the probability amplitudes of the different states into the marked states that you care about. And I believe there is, someone can correct me, I believe there's a mathematical sense in which that does look like a diffusion operator, but intuitively, like, that's the diffusion that's happening. Good question. It does, yes, okay, right. Yeah, right, exactly. Okay, yeah, so it is a proper diffusion operator in the right formalism. Excellent. Okay, so we've managed to define our entire circuit for Grover's algorithm. Now we can run it. Let's do real quantum computing and put Dr. Grover and colleagues to the test. So we'll create our backend object as before, and I won't dwell on this part, but I'll just mention when we run our optimizer this time, it actually will do a little bit of work. I won't dwell too much on it, but we have a complicated circuit now, and if I transpile my circuit to run on my target simulator backend, you can see that some of these gates are new. These are basis gates, or gates that are in the basis gate set of the air simulator. So U1 and U2 are some special rotation gates, and they've got some parameters and angles and stuff in here. We don't need to dwell on it, but just as a note, the optimizer, the quantum transpiler, is actually doing some meaningful work here since the circuit is non-trivial. Okay, but anyway, that point being said, we'll actually go ahead and run stuff now. So as we did with our previous example, we're going to use our perfect, happy little noise-free simulator. We'll transpile our circuit to run on our backend. There it is. And then we'll use our backend to run our transpiled circuit. And we'll do this for 1,000 times. Note that this 1,000 times, this is not the number of iterations within Grover's algorithm, that T, that optimal number of iterations. This is like how many times you run the entire algorithm. Because even Grover's algorithm, when you run it for the optimal number of Grover's iterations, it's probabilistic. You have high probability you'll get the answer you want, but it's not guaranteed. So you have to run the whole algorithm some number of times, like 1,000 times. It's sort of the back of the envelope thing a lot of people use when they don't know better. To see how this looks. The rest of this code, where we just look at the results and plot it, same as before. We'll copy paste it from our other example here. So here we go. All right, what were our marked states? I sure hope our marked states were 0, 1, 1, and 1, 0, 0, because that is what we observed here. So when we run Grover's algorithm for 1,000 times, here are the results we get. 523 of the times we get 0 and 1, and the rest of the time, the rest of our 1,000 runs, we get the other marked state. So Grover's algorithm, lo and behold, looks like it actually works. Grover was not lying. We actually can use this algorithm to identify our marked states from among all the possible states. So that's good news. But there's something lurking in the background that we have not covered. It's been sitting there the whole time, and that's noise. Everything we've done so far has been on a perfect noise-free simulator. And of course, if you take this algorithm and run it on a real quantum computer, this is like a theme you've heard of for 3 days, right? We have clusters on the wall, all about noise and error correction, right? So what we can do is actually simulate what that noise looks like, which is kind of cool with Qiskit. So obviously, we could run it on a real machine, like I mentioned, and see what the actual results look like on a real quantum computer. But what IBM has done, which is actually pretty nice, they've run a bunch of experiments on their actual hardware, of course, and so they've generated the noise profiles of what noise looks like on their various devices. So the IBM Vigo machine was, I think, 2 or 3 machines ago. It's not the newest one, but it's relatively recent. And so within Qiskit, in this Qiskit IBM runtime package, which is specific to IBM providers, we have a fake Vigo V2 model. And so this is going to be a back-end object that emulates the noise and behavior of what it would look like if you ran your problem on the Vigo hardware, the actual machine itself. But we can do this just classically simulated, et cetera. So for free, but with the same benefit of seeing what that noise looks like. One little bit of sort of Qiskit notation we have to deal with is that we create this device backend, this device object, but to create the actual backend that we run our job on, we have to create a simulator object from that device backend. So we create a simulator backend from the device backend You just have to bear with me on that one. That's just the way Qiskit is. But believe me on that point. So we'll use our device backend to create a simulator backend using this device or noise profile. And then everything else is copy pasted. So we transpile our circuit this time onto our new simulator object that's using this fake Vigo backend. And then we'll run on this simulator backend. We'll go ahead and run our circuit. We'll do it for 1,000 times, plot the results. Okay, I'm not feeling too good. There's gonna be a lot of noise. Let's see what happens. I feel like we need a drum roll or something. Here we go. All right, it's too fast for a drum roll. Here are our results. And lo and behold, it's not too bad, okay? Like, we're actually doing okay. For all the hype and fear we've heard about quantum noise, right? You can pretty clearly pick out the correct results, right? And they are the correct results. They're the two marked states. So the two marked states, looks like we get them about 73% of the time, right? And the other 27%-ish of the time, we're getting stuff that we don't want, which is not great. 1 in 4 times-ish, this algorithm is sort of failing just due to noise, not due to any randomness or whatever within the algorithm itself. But again, sort of understood in the QC community, like you're going to have to run your algorithm 100 times or 1,000 times and then do some sort of voting procedure. And you can do like a totally classical voting procedure, right, or have a threshold. You could say anything that was seen less than 100 times is fake, or maybe you know that there were 2 items in your database you're looking for, so just pick the most popular 2. Different, classical heuristics, whatever you want to do to say like these are the answers and these are not. So again, even though we added in some realistic noise of a quantum computer here, we were still able to ascertain the correct results of Grover's algorithm, which is pretty good news. But this is only a 3-qubit example, and there are only 2 marked states. So obviously the search space here grows exponentially as you increase the number of qubits, right? So we had 2 to the 3 possible outcomes, and with even just 3 qubits, 2 to the 3 outcomes, we're wrong like a quarter of the time. And so you can imagine with like a 32 qubit system, suddenly we're gonna need error correction. These amplified amplitudes, the answers that got kicked up during Grover's algorithm began to look just sort of like the noise that you get. So it becomes really hard to differentiate what's real and what's noise for those larger systems. So for demo purposes, 3 qubits, you really, honest to goodness, can run this on an IBM machine and do real quantum computing with Qiskit, and it works. For larger qubit counts, you run into more noise and more problems. Awesome. So that is everything we have to give you a flavor of Qiskit and running some real quantum computational problems on there. I'll leave the notebooks up here, URLs up here again for your pleasure. We'll also send out these slides and stuff if you want to play with them at home, and our emails are up there as well. But otherwise, we'll float around for a few minutes for questions, and thanks so much for your time. And Anne-Marie, are we over or under? Do we have time for a question? Or?
Okay, we could do a question. We're trying to keep us in line with their timing over there, but we can do, yeah, go ahead.
Yes, I'm just curious. So like, let's say you wanted to run on a different architecture than the IBM. How would you work with Qiskit? If you just generate a CASM file from it, or how can you?
Yes, so with Qiskit, the question is how do you run on stuff that's not from IBM with Qiskit? So Qiskit you can export to like an OpenQASM file or something, a different sort of intermediate architecture that other libraries could run. Qiskit also allows you to write providers for other machines. So if you're able to write a provider for your Bob's QC machine that is compliant with Qiskit's device API, you can just go ahead and use Qiskit for other devices too. That's been kind of the vision of Qiskit, is to make it device agnostic. It's sponsored by IBM, and other companies have their own libraries, so like it's not really as super device agnostic right now as you sort of would like it to be. But in a couple of years, if Qiskit remains the dominant thing, all these hardware providers can plug in their backends into Qiskit, and then you can use that one API for everything. I believe there's a few of the big companies. I don't know off the top of my head, but I think there are a few other companies aside from IBM where you can use Qiskit to actually run on their hardware right now.